Hello. Welcome to Gaslaws by Charlie Noble, Dan Levitt, Andrew Perella, and Steve Powell. Boyle's law simply states that when the pressure of a gas increases, the volume of a gas decreases if the temperature is held constant. The equation describing this law is P1 times V1 equals P2 times V2. The mathematical relationship is indirect.
If a gas at 25 degrees Celsius occupies 3.6 liters at a pressure of 1 atmosphere, what will it be its volume at a pressure of 2.5 atmospheres? In order to solve this problem, we need to know what we are solving for. So we know that when the pressure is at 1 atmosphere, the volume is at 3.6 liters. So P1 equals 1 atmosphere, V1 equals 3.6 liters. Then we know that P2 equals 2.5 atmospheres. That means we are solving for V2. To solve for V2, we will multiply P1 by V1 and divide that by P2. So we will plug that into our equations, and we get 1 atmosphere times 3.6 liters, all divided by 2.6 liters. We will use significant figures, and the answer to the problem is 1.44 liters.
Charles's law says that the volume of a fixed mass of gas is directly proportional to its Kelvin temperature if the pressure is kept constant. So as temperature increases, volume also increases. So when temperature decreases, the volume also decreases. It is defined by V1 over T1 is equal to V2 over T2.
What change in volume results if 60 milliliters of gas is cooled from 33 degrees Celsius to 5 degrees Celsius? To solve this problem, we again need to know what variable we are trying to solve for. We know that the starting temperature is 33 degrees Celsius, but we need to convert this to degrees Kelvin. To do that, all you have to do is add 273 to the degrees Celsius, and you get degrees Kelvin. So we do that for both of the given temperatures, and we know that T1 equals 306 Kelvin, and T2 equals 278 Kelvin. Then are told that V1 is 60 milliliters, so we are solving for V2. By using simple algebra, we know that Charles' law says that V2 equals P1 times T2, all divided by T1. When we plug in the numbers, we get 60 milliliters times 306 Kelvin divided by 278 Kelvin, which equals 66 milliliters using sig figs.
Gay-Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature if the volume remains constant. As temperature goes up, pressure goes, and as temperature goes down, pressure also goes down. The mathematical relationship between temperature and pressure is direct. The law is represented by the equation P1 T1 equals P2 over T2.
Determine the pressure change when a constant volume of a gas at 1 atmosphere is heated from 20 degrees Celsius to 30 degrees Celsius. As we know, the Gay-Lussac law is P1 over T1 is equal to P2 over T2, and we will use this to solve the problem. The problem tells us that T1 is equal to 20.0 degrees Celsius, and T2 is equal to 30.0 degrees Celsius. But we need to convert that to Kelvin, so 20.0 plus 273 is equal to 293 Kelvin, which is T1, and 30 degrees Celsius plus 273 Kelvin is equal to 303 Kelvin, which is equal to T2. Then we are told that P1 is 1 atmosphere, so we use these to find P2. Using the law, we know that P2 is equal to P1 times T2 divided by T1. When we plug in all these numbers, we get 1 atmosphere times 303 Kelvin divided by 293 liters. This equals 1.03 atmospheres.
The combined gas law describes the relationship among the volume, temperature, and pressure of an enclosed gas. The variables involved in the law are temperature, pressure, and volume. The combined gas law is represented by P1 times V1 over T1 equals P2 times V2 over T2.
A 320 centimeter cubed sample of helium gas is collected at 25 degrees Celsius and 99.3 kilopascals. What volume would this gas occupy at standard temperature and pressure? In order to solve this problem, we must first know which variable that we are looking for. We are told that V1 equals 320 centimeters cubed, and T1 equals 25 degrees Celsius, and P1 equals 99.3 kilopascals. Also, according to STP, we know that P2 equals 101.34 kilopascals, and that T2 equals 273 Kelvin. That means that we are solving for V2. But before we can solve for V2, we need to make sure that we have the correct units first. All you need to do is convert 25 degrees Celsius plus 273 equals 298 Kelvin. Using the law, we know that V2 equals V1 times P1 times T2 over P2 times T2. Then you just plug in the numbers and you get 320 centimeters cubed times kilopascals times 273 Kelvin divided by 101.34 kilopascals times 298 Kelvin. Using the proper number of sig figs, you should get V2 equals 287 centimeters cubed.
The ideal gas law uses an imaginary gas that conforms to all the assumptions of kinetic molecular theory. To calculate the number of moles of the contained gas, we use the variable n. R is the ideal gas constant, which equals 0.0821 liters atmospheres per moles Kelvin. PV equals nRT is the equation used to represent the ideal gas law.
A helium-filled weather balloon has a volume of 240 liters at 99 kilopascals and a temperature of 0 degrees Celsius. What is the mass of the helium in the balloon? To solve this problem, we need to know which variable that we are looking for. So we will do this by defining all the variables. The problem tells us that V equals 240 liters and that T equals 0 degrees Celsius. But we will be using 273 degrees Kelvin. We will also know that the pressure is 99 kilopascals, but we have to convert that to atmospheres. So we will divide 99 kilopascals by 101.34 kilopascals to get 0.977 atmospheres. R is a constant, and we know that is equal to 0.0821 liters atmospheres divided by moles Kelvin. So after defining all of the variables, you know that you are looking for N, or the number of moles. To find, we will use N equals PV divided by RT. When we plug then numbers in, we get 240 liters times 0.977 atmospheres divided by 273 Kelvin multiplied by 0.0821 liters of atmospheres divided by moles Kelvin. The answer using the correct number of significant figures is 10.5 moles. Use the units as a way to check your work. Here's some useful information. Temperature of K equals temperature C plus 273. That is the temperature of Kelvin. 1 atmosphere equals 760 millimeters of Hg, which is torrs, which equals 101.43 kilopascals. Molar volume is at STP, which equals 22.4 liters.